So most electromagnetic launchers have found applications in national defense, such as linear induction motors used for electromagnetic aircraft launch systems, and railguns used for close-in weapons systems. However, EML for space launch has more to do with higher-level geopolitical goals. That is, proving that you have the best strategies, technologies, and economic systems for advancing human civilization. To prove to the rest of the world that your way of doing things deserves support, it's important to occasionally achieve some historic geopolitical milestones. Wins, such as sending the first humans to space, landing the first humans on the moon, or successfully cooperating with other countries to build an orbiting research lab. Overall, it's about winning the hearts and minds of people around the world and inspiring the next generation. The next frontier in space is not low Earth orbit, it's further away from Earth. The next frontier is the Moon and Mars. And this is key because electromagnetic launch for space travel becomes more relevant, more pivotal, as the frontier moves further away. When space transportation is governed by the rocket equation, the mass ratio is proportional to the exponent of delta V. Empirical data shows that the cost per kilogram, like the mass ratio, also scales exponentially with delta V. This exponential relationship between cost and delta V makes one-way and round-trip transportation to the Moon and Mars incredibly expensive, even though delta V requirements for the mission increase by only 50 to 100%. For the one-way trip to Mars, for example, we're in the $1 million per kilogram range. And for a round trip, we're in the $1 billion per kilogram range. The exponential relationship between delta V and cost is captured by this formula. For example, sending the mass of the International Space Station, which is about 450 metric tons, on a one-way trip to the surface of Mars would cost $450 billion. A crew of 6 at about 100 kilograms per person, not including provisions and water, will cost about $600 billion for the round trip. The launch portion of NASA's human spaceflight budget is currently only about $8 billion per year. So while chemical rocket technology is good enough for sustaining one-way and round-trip resupply trips to the International Space Station, which is in low Earth orbit, it's too expensive for similar trips to the Moon and Mars. Congressman Dana Rohrabacher said, or summed it up nicely when he said, talking about NASA's strategy for going back to the Moon, "There's nothing new or innovative in this approach, especially for the outrageous price tag." And that's the real tragedy. Nostalgic rocketry is not how great nations invent their future. And mass drivers can also be expensive, but the cost-velocity relationship is not exponential. Most mass driver designs can be characterized by cost equals K1 times V squared plus K2 times V cubed, where cost here refers to the capital cost and delta V represents the muzzle velocity of the mass driver. Now, the first term captures the idea that the length of the mass driver will increase with the velocity squared, because basically from high school physics, V squared equals 2AX. So a portion of the cost is proportional to the length of the mass driver, which is logical. There's also a relationship between the cost of some of the hardware that adds kinetic energy to the vehicle and delta V. And that is best characterized by a cubic relationship. And this is captured by the second term. Now, the derivation of this cost equation, I could go through it, but if you just want to take a picture of the slide, it'd be better. I'll put this into the paper rather than walk you through the derivation. But this explains the cubic relationship related to power electronics and the conversion of stored electrical energy into kinetic energy. So electromagnetic launch for space transportation becomes relevant if it brings the cost of a space program that culminates in a geopolitical win, a historic win, in line with the country's space exploration budget. For EML to be relevant, the space program cost with a mass driver must be a lot less than the cost with an all-rocket system, because the all-rocket system is far too expensive right now. If we substitute the cost formulas from some of the previous slides, we can see that the key to making this happen is to minimize K1 and K2 in this equation at the bottom here. But especially K2, the coefficient of the V cubed term. Now, due to orbital mechanics, delta V for these kinds of missions is in the range of roughly 11,000 to 20,000 meters per second. So we have to be working in that range to optimize this equation. And this depends on the nature of the mission, whether it's a one-way trip or a round trip to the moon or Mars. If we were to work out the K1 and K2 values for the EMALS launcher that's on the, I think it's the JFK, the Kennedy aircraft carrier, and then scale the delta V in that equation to, for example, 11,000 meters per second, which is what you would need to go to Mars, or a Mars transfer orbit, the cost would be ridiculous, probably in trillions of dollars. And the reason for this is mostly concentrated in the V cubed term of the equation, not in the V squared term. The question then becomes, is there an architecture for a mass driver where K2 is much smaller, and so that we can scale the technology up to the point where it's useful for space launch? And this is a question that we've been investigating. And what we came up with was an architecture called, or based on, a variable pitch screw. This mass driver design has two counter-rotating screws, two counter-rotating variable pitch screws. The screws are made up of many individual screw segments, which are supported by brackets. Now this, by the way, is going at 1/100th normal speed, just so you can sort of see what it looks like. Electric motors inside the screw segments rotate the screws at a very high RPM, and the brackets also support a rail, and the magnetically levitated sled carrying the vehicle will travel down the rail between the screws. On the sides of the sled, there's a system of actuators called grapplers. These grapplers engage with the screw flights to accelerate the sled forward. And at the ends of the grapplers, there's these electromagnetic pads, which are colored green. These electromagnetic pads are magnetically attracted to the backs of the screw flights, but they never make direct mechanical contact with the screw flights. While the electromagnetic pads are hovering behind the screw flights, they're always on. They're not turning on and off. They're arranged in a homopolar configuration as well to minimize eddy current losses. Now, the variable pitch twin screw design does not rely on rapidly switching electromagnets on and off in series as the vehicle travels past. Acceleration is achieved by essentially surfing on the mechanical wave of the counter-rotating twin screws. So kinetic energy stored within the screws is transferred to the sled and then to the vehicle, but the energy transfer does not involve implementing a linear electric motor. It's more like a magnetic gear. To help inform our understanding of the cost and to refine the design, we've been constructing the first in a series of small-scale prototypes. In fact, most of the detailed design work has been done by Alistair here. He's here at the conference. Say hi. Be sure you find him if you want to ask any questions later about the design. This prototype has brushless DC motors housed within 3D printed variable pitch screws. These are the screw segments. For this small scale prototype, we opted to go with a mechanical connection between the screw flights and the sled. However, we have a developmental roadmap that outlines a series of prototypes which are more complex, larger, and more full-featured, and will gradually progress towards the full-scale version through that series of prototypes. The full-scale version has been implemented, however, as a digital twin and uploaded to GitHub. So the digital twin was used to create the animations you saw a few slides back. This chart here also shows some of the telemetry from the simulated launch. The digital twin also includes cost estimation math. So this chart is listing a few of the design parameters that come from the digital twin. There are currently 659 such parameters in the digital twin, so I couldn't show you all of them, but these are the most interesting ones perhaps. I think the most interesting is the capital cost, which is calculated to be $32.6 billion US. And this is a very detailed calculation that came up with this number. And this value is much more in line with the collective annual budgets of space agencies that might collaborate on a space program to go to the moon or Mars, for example, similar to the Artemis program. There's a lot of aspects of this design that I don't have time to cover in today's presentation. However, if you're interested in learning more, I did give a longer presentation at the International Space Development Conference in Los Angeles back in May of this year. This video, which you can take a picture of the QR code if you like, has 123,000 views on YouTube. And as a bonus, there are dozens of harsh comments under it that express all kinds of doubt as to whether the law would work. But to conclude, electromagnetic launch is not just for weapons. We wanted to figure out if it was potentially relevant to historic achievements in the geopolitical arena. key to this is to select an architecture that scales well with the kinds of speeds we need for space travel. It doesn't get too expensive with these high speeds. And the key to that is eliminating the components where the cost scales with the cube of the velocity, which is basically the power electronic components. Or let's say components involved in converting electrical stored energy into kinetic energy. The variable pitch screw launcher is an example of this architecture. It currently is supported by a sophisticated digital twin and an early physical prototype. And the cost estimate for a full-scale version capable of launching spacecraft directly to Mars transfer orbit is $32.6 billion, which is in line with what space programs can afford to do for a space program over several years. Therefore, our findings are that electromagnetic launch is highly relevant to space launch and also to the next big achievements in the history of spaceflight. Thanks very much. If you have any questions.
Thank you.
On one of your last slides, I was trying to think about the acceleration and then I couldn't find that, but did I see that the length of your track might be 700 kilometers long?
Yes.
Okay. Yeah,
so it's 700 kilometers long, but so keep in mind the cost calculation considers all this.
Yeah.
The screws themselves are not that expensive per meter compared to perhaps an EML type launch system where there's actual electromagnets in the launcher. So these are just mechanical rotating screws, which are fairly cheap to produce per meter.
And what would the acceleration be over that length? Yeah,
so this slide here gives you all the telemetry. The acceleration in this particular simulation was 8 Gs for the horizontal part, where you're just going straight forward up on the variable pitch screws, followed by a very short 12 G ramp acceleration, where you're being accelerated upwards on the top side of the mountain, basically. I think that was about 8 seconds or so in time. The assumption here is we make acceleration couches that are very well designed to support the people in them so that they don't die, and they may pass out, but they're probably fine.
Thank you.
Yeah, that's a good question. I don't have that number on the top of my head. I did write a paper which got published in IEEE Aerospace back in 2023, early 2023. I can give you that reference later, and I think it has some numbers in there that talk about the torque or the stresses on the grapplers and the arms. But you're right, that is an actual area, not so much from the mechanical stress point of view, it's quite high, but one of the key parameters or challenges in this design is the magnetic coupling stress. So the magnets that are on the back of the screw flights, initially there's not much of a problem, but as you get to very, very high speeds, the pitch of those screws becomes very steep, and the screws are sort of pulling away or parting. The magnets behind them have to kind of stay attached. They have to pull the vehicle forward despite the very high slope. So it's a bit like pinching a watermelon seed in reverse. The vehicle moves a lot forward for small distance horizontal change in screws, and that leads to a lot of force. It has to be managed, but it is manageable within current engineering technology.
Follow-up question: 700 kilometers is inclined or flat?
Flat.
Flat, but then the civil work to make a flat 700 kilometers is in account in the calculation, because 700 kilometers of flat land.
Oh, it's actually, I didn't show that, but it's actually in a tube that's under the surface of the ocean. So the idea is you build a concrete tube, and inside you put a steel tube, and you submerge that just far enough down that ships can pass overhead, so maybe 10 meters, 20 meters down. So the waves are no longer a problem, and you anchor it to the seafloor, and that's what your 700 kilometer part looks like. It's just an underwater tube anchored to the seafloor. And then the ramp part is on land, and there's tunneling costs. So we basically said, we'll just tunnel under a mountain and come out the other side. And so we just calculated the tunneling cost for that. I think that was, I forget the exact number, but it was, ramp length is 82 kilometers of tunnel. It's not a very big tunnel, but it's 82 kilometers of tunnel. Yeah.
So here I have one question.
Sure.
And you have a very long way to go. And do you have a distributed power supply or just an integrated one?
Yeah, so the power supply in this isn't like a normal electromagnetic launch power supply is going to transfer a lot of power from energy storage to the vehicle in a short period of time. This one has this, power motors that gradually spin up the screws.
Only one, the start and the end.
No, all the way along. Every screw segment has a motor inside it. Like you say, like a motor from a Tesla car, for example, like an electric motor. And that will spin up the screw flight, or the screw segment, to a very high speed. But it's got lots of time to do it. So it could probably spin it up over an hour of time to full speed. So there is some energy needed to do that, but it doesn't require a lot of power. It just requires a lot of energy over a long time.
Okay, thank you.
Yeah.
So, thank you, Philip.
You're welcome. Well, I think there's another question.
Okay.
There's time.
When it is traveling in a very high speed, the heat generation due to the friction will be significant.
Which friction? Air friction?
Heat generation due to friction.
Yes. Now, which friction are you referring to? Friction between mechanical parts
You
or air friction?
use a screw
Yeah,
as a traveler, so the friction will be, I think, will be very large.
Right.
And
Let me correct you on that.
Mhm.
So the launcher is traveling inside a vacuum tube.
Yes.
That part is all in a vacuum, so there's no air friction inside the tube. There is no mechanical contact between the grapplers and the screws. It's a magnetic attraction, and there's an air gap. Or a small air gap, but there's an air gap there, so there's no actual mechanical contact.
No friction.
No friction.
Okay, thank you.
Zero air, zero friction, provided everything works. Okay.
Okay, so, thank you.
Yeah. This presentation was one of many given at the 20th International Symposium on Electromagnetic Launch Technology, a 4-day conference that took place in Amsterdam at the end of September 2024. The venue was the same building that once housed the world's first stock exchange. This was a conference with lots of attendees who prepared high-quality and very technical oral presentations and poster sessions. Short conference papers will be published as proceedings on IEEE Explore. Some longer form papers will also be published in a special issue of IEEE Transactions on Plasma Science. The next conference, the 21st International Symposium on Electromagnetic Launch Technology, will be taking place September 13th to 17th, 2026 in Nagaoka, Japan. Other conferences coming up include the Reinventing Space Conference in London this November, which is put on by the British Interplanetary Society, and the International Space Development Conference, which is hosted by the National Space Society. That will take place in Orlando, Florida in June 2025. The abstract window for this conference is still open, so if you're actively working in this field, please consider submitting an abstract. That's all the announcements I have. As always, please check the description for any errata. Hopefully you found some of the material covered in this presentation to be valuable. Did any of it align with your own knowledge and experience? Do you know of any developments in this field or any other conferences that cover space infrastructure? If so, please let us know by leaving a comment below. Finally, thank you very much for your continued support and engagement, and I hope to see you all again soon.